We're going to be talking about complex ions. Generally, because this is kind of an unusual topic, this comes up when we talk about solubility, because when a complex ion can form, that can increase the solubility. If you add the ligand, that will increase the solubility of the metal ion as a part of the complex. So this is just some general information about complex ions. Here we have cobalt in the center. There's a central cation, a metal cation. These on the outside, these ammonias, are what we call ligands. They are attached, and there's a variable number of ligands. They can be neutral molecules like you see here, or they can be ions, like chloride ion is a ligand that you sometimes see. These ligands are attached through coordinate covalent bonds. A coordinate covalent bond is a covalent bond, but it's one where the electrons are both donated by the same atom. So this term up here, coordinate covalent bond, is a covalent bond in which both of the shared electrons are contributed by one of the atoms participating in the bond. In the example you see here, ammonia, if you draw the Lewis dot structure for ammonia, you get the central nitrogen with 3 attached hydrogens. That central nitrogen has a lone pair of electrons on it. That lone pair is donated, in this case, to the cobalt to form that covalent bond. And then that each of those 6 donated electrons form 6 coordinate covalent bonds. So there are 6 ligands attached, in this case, to cobalt-3 ion. The number of ligands varies. The charge in the central atom varies. The charge of the ligands will vary. And so all of those will influence the properties of this complex ion. Different central atoms can bind different numbers of ligands. That concept is a little bit beyond the scope of this class. A normal covalent bond that we typically think about, if you have a hydrogen atom with 1 valence electron and it wants to form a covalent bond with another hydrogen atom, each atom brings 1 electron with it, and then they sort of mutually share those 2 in the covalent bond. So coordinate covalent bonds are a little more unusual, where 1 atom donates both electrons. Here we have the cobalt ion in the middle, and then the ammonia with its lone pair. This arrow is drawn from the nitrogen, from the electrons, from where they're going to where they're going toward, where they're coming from to where they're going toward. So these orange arrows we draw, they form the bond. The cobalt in the center is considered a Lewis acid. It is an electron pair acceptor. The ammonia, each ammonia in this case, is a Lewis base. It's an electron pair donor. So the Lewis definition is really a little bit more general a definition. These are some examples of pictures and structural formulae of complexes. Remember that the wedges come towards you and the dashed lines go back into the screen, so they should both all sort of be somewhat of a 3-dimensional view. These all have different structures, different geometries. Oh, it looks like I'm modifying my cobalt. It was supposed to be 3+, and I made it 2+. I kind of thought that when I was saying it. Cobalt can be 2+, but in this particular case it's a 3+. So now when we write the overall formula, since the ammonias are neutral, the overall charge is still +3. The water molecules in the lower left hand in this complex ion at the bottom, this is a cobalt +2 ion with 6 water molecules attached. So you get cobalt, you get the water in parentheses with a 6, and the overall charge is +2. In the center we have an iron 3 and 6 waters attached. The waters are neutral, so the overall charge is +3. Zinc with 4 ammonias attached in the upper right hand corner with +2, and then a copper with 4 ammonias attached, and it's an overall charge of +3. So the central ion in each case I'm underlining in orange, and then the ligands I'm underlining in green. The overall charge is a combination of both of those. In all those cases, the ligand was neutral, but you can have a ligand with a negative charge or some charge, and then the overall charge of the complex ion would be a combination. It would be the net overall charge. So now let's talk about solubility and complex ion formation. So the question here, what does complex ion formation have to do with solubility? Why do we care about this? So if you look at the solubility equilibrium on the top, we're trying to dissolve silver chloride. It has a relatively low KSP, which means it's relatively insoluble in water. Below that is the complex ion formation equilibrium, where a silver ion will combine with two ammonias, and that will form the silver ammonia complex ion. This is the formation constant, 1.7 times 10 to the minus 7. It's relatively large, lies pretty far to the right. So what this all means is that silver chloride is more soluble in ammonia than it is in pure water. So the reason for that is because the solubility equilibrium at the top is influenced by the complex ion equilibrium underneath. So if we're trying to dissolve silver chloride in water, we see it isn't very soluble, which there's the sad face there. So if we add ammonia, then the reaction on the bottom will occur, gangbuster style, right? Far to the right, 10 to the 7. What that's going to do is it's going to remove silver from the solution. That's going to decrease the silver ion concentration, and that's going to influence the equilibrium on the top. Le Chatelier would say that if you remove product, then the equilibrium on the top will shift to the right, which is the soluble side, right? So if Le Chatelier were here, he would say this makes complete sense because product removal should shift the silver chloride dissolution reaction, the one on top, to the right. There's Le Chatelier again. Le Chatelier just comes back over and over and over again. Good guy, we like him.